Hello everyone, this is the second lecture on the topic of unsymmetric bending of beams. So in this lecture we are going to discuss some of the important steps that we need to follow while solving various kinds of problems on this topic. So what do we even mean by solving problems? Well, in order to understand that, we need to quickly refer to the first lecture that we had on the previous day. So if we go back to the development of the mathematical framework that we were discussing the other day, we'll see that what we ended up deriving was basically first the formula for the orientation of the neutral axis, and then another formula for the bending stresses, the sigma xx. So let's take a quick look at that. So here we have the tan beta. So let me just highlight this. This is the tan beta, where beta is the angle that the neutral axis makes with the y-axis of the cross-section. So in order to understand that, we'll quickly refer to the diagram that we had drawn the other day. So this was our fairly complicated diagram, and you can see that we have the y-axis here, and this yellow colored dashed line, which was superimposed by the purple colored z dash axis, that was our neutral axis. And you see that the angle that this neutral axis makes with the y-axis, that is denoted by this beta. So the formula that we had derived, tan beta, gives us the orientation of the neutral axis. You please note that this formula includes the geometrical parameters Iy, Iyz, Iz, as well as the values of the moments My and Mz, both in the numerator as well as in the denominator. Next, we had gone on to develop the formula for the bending stress, the sigma xx. And let me just highlight that for you again. So this was our fairly big formula for the sigma xx. Now, let us remind ourselves very importantly that both these formulas, in fact the entire mathematical framework that we had developed the earlier day, it was solely pertaining to the case of the pure bending of beams. However, we did not restrict ourselves to any particular cross-section. It was meant for any general cross-section. The other important thing was that the y-axis and the z-axis that we were considering were centroidal axis. That is, they both passed through the centroid of the cross-section. Okay, so when we today when we want to discuss problems or the key steps, the primary steps that we should be following while solving our problems, what we basically mean is that we want a prescription or a recipe to follow in order to be able to find out the value of sigma xx at any given location within the cross-section, given certain values of the bending moments. So in terms of the formula, what we want to find out is the value of sigma xx, is the value of this sigma xx at any particular y and z, that is at any particular point within the cross-section, given certain value of the bending moment, that is certain combination of this value of my and this value of mz. Please note that for a given cross-section, the values of Iyz and Iz will be a constant. Again, if we look back at the tan beta formula, we'll see that it also contains the mz, my, and of course the Iy, Iyz. Now, when we want to develop the steps when we want to note down the steps, first and foremost thing that we have to do is to find out the values of these geometrical parameters, that is IY, IYZ, IZ, as far as we are concerned about finding the tan beta. Similarly, for the sigma xx also, our first job is to find out the value of this IYZ, IZ, and IY. Because in any given problem, or in any problem, the MZ and the MY values would be given because that is the externally applied load. Furthermore, we would be interested at a particular location, so the Y and the Z values would also be known to us. So, in today's lecture, what we'll be basically doing is to talk how to find out these second moments of area. Now, this seems like a very easy thing to do, especially if we remember what we had already done or covered in our undergraduate classes. But please note that we are no longer considering very nice symmetrical cross sections. So we would be interested in real world engineering cross sections, which could be very nicely doubly symmetric, like a rectangular cross section or a square cross section, or even a perfectly symmetric cross section like a circular one. But it is also very much possible that the cross section may not have any symmetry at all. So towards that end, what we would like to do is to first start off very quickly with the rectangular cross section only, but we'll see that some key point which we'll have to note. So, so the first step So the first step is basically that we need to find out the centroid of the cross section. Find the centroid of the cross section. Why is this the first step? Because you note that the entire mathematical framework that we had developed in the previous class referred to y and z axis which pass through the centroid. So if we take a quick look at the previous diagram, so here both the y-axis and the z-axis, they passed through this centroid. So this was the centroid of the cross section. So if we have to use the formulas that we had derived in the previous lecture, we need to consider centroidal axis. Okay. The next thing that we need to find out the second moments of area. Now, both these steps could be a little bit time consuming, but things can be made fairly simple or simpler if we proceed in a very nice step-by-step fashion. So towards that end, what we'll do is to first consider the simplest of cross sections, which is the rectangular cross section. Of course, a circular cross section will be much simpler than that, but we'll not consider that. So going ahead, we'll first consider a rectangular cross section. Okay. Now, the first step, as we had mentioned in the previous page, was to find out the centroid. And we all know that the centroid would be lying at at a distance which is halfway between the two parallel vertical edges as well as the two parallel horizontal edges. So the centroid would be somewhere here. Now, this kind of a discussion is all right as long as we are doing a qualitative discussion, but while solving problems, we need to have a proper recipe in order to obtain nice quantitative values. So what do we do? Well, the first step that we do is to imagine that our origin is at the left corner here. So we imagine that our origin is here, because right now we have not even set up our coordinate axis that we would actually need to use to solve our problem towards finding out the orientation of the neutral axis and towards finding out the bending stresses. Because again, I remind you that we have to set up our coordinate axis passing through the centroid. So we need to first locate the centroid. So towards that end, the centroid would be located in reference to this point. It is very much possible to have the starting origin here, 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 or anywhere else, but to keep things simple and systematic for the purpose of our discussion today, we'll consider the origin to be placed here. Okay, so if this width is W, and let me use this as the breadth. So I'll call this as B instead of W. I'll call this the breadth, and this as the height. H denotes the height. So we know that the centroid would be located in reference to this origin at B by 2 and H by 2. Now, the moment we recognize that the centroid is located here, what we'll do is we'll set up our coordinate axis. So we'll set up a pair of centroidal axes in this fashion. So this will be our y-axis and z-axis. Now, we all know that in this particular case, the value of Iz would be 1 by 12 BH cube. Iy would be 1 by 12 B cube H, and Iyz will be equal to 0. So this was a fairly easy example. We all know about this. But to go ahead, we would need a recipe to use these simple ideas in more complicated situations. So the first step towards that would be to realize that if we have a rectangular cross section, but where the y-axis and the z-axis are not passing through the centroid, then what are the values of Iz, Iy, and Iyz? So what I'm saying is that if we have a rectangular cross section like this, and we have our z-axis and y-axis in this fashion, then what would be the values of Iz, Iy, and Iyz? Now, one may wonder that if our entire mathematical framework is developed for the case where we are only bothered about centroidal axis, why are we even considering a pair of axes, coordinate axes like y and z, which are not even lying within the cross section? So the motivation for this particular discussion is that some real world engineering cross sections, beam cross sections, would be composed of a composite of such rectangles. So we'll discuss that in the next page, but for now we'll just quickly take a look at what happens to the values of Iz and Iy for this particular setup. So we have the same kind of breadth and height as before, but very importantly, we recognize that our centroid is still here, and the distance of a pair of axes, of a pair of centroidal axis. So let's say if we have a pair of centroidal axis like this, so let's say this is y dash and z dash, so these are centroidal axes. So what is the distance between z dash and z, and what is the distance between y dash and y? So let's denote this by, so this distance by dz, and this particular distance between the y dash and the y axis by dy. So in this situation, our Iz will be basically formed from a contribution by considering the centroidal axis as well as the actual axis that has been given to us. Please note that the Iz that we are considering is with reference to the given z axis, which is the red colored axis here. So first of all, refer to the z dash axis. What we have is 1 by 12 bh cube, just as before, but this is only in reference to the z dash axis, that is the centroidal axis, which is not the given axis. So in order to find out the correct value of Iz, refer to the given axis. What we need to do is to use the parallel axis theorem, so that this will be plus the area of the rectangle, the area of the cross section, which is BH, times the distance between the z dash and the z axis squared. So this will be dz squared. In a similar fashion, if we talk about Iy, it will be 1 by 12 b cube h plus the area of the cross section, which is BH again, and the distance between the y dash and the y axis, which is dy, square of that. Finally, for our Iyz, we have first of all the zero contribution by referring to the centroidal axis y dash and z dash, but refer to the y and z axis, we have the area of the cross section times the distance between the y dash and the y axis, which is dy, times the distance between the z dash axis and the z axis, which is dz. So overall, this is what we have to do when referring to this kind of a setup. So let us take a look at where this kind of an application would be useful. So the first cross section that we are going to consider would be something which is fairly common in real world engineering practice, and it is something like this. Okay, so this is this looks like an L, and this is the shape of the cross section, and you understand that the beam is into the plane of the into the plane of this screen here. So how can we apply the concepts that we had developed in reference to the rectangular cross section earlier? So the idea sphere is quite simple. What we need to do first of all is to think of this rather unsymmetrical cross section, this unsymmetrical L cross section, as being composed of two rectangles. So what we do is we take an imaginary cut through here, and then we say that this L section is composed of this rectangle and this rectangle. All right. So how does this step help us? Well, you see, if we refer back to the important steps that we need to follow while solving the problems of unsymmetrical bending, our first job is to find out the centroid, and the second one is to find out the second moments of area. Now, coming back to this L shaped cross section, to find out the centroid of this cross section, starting from those integration formula that we had discussed at the beginning of the previous lecture, is not so easy. What is easy, however, is to consider how we may find out the centroid by considering it to be composed of these two rectangles. So what we can do is, in order to find out the two coordinate points which would be representing the centroid, we first start by imagining that our starting origin is here. It is absolutely possible to take our starting origin at any other point, but just to keep the discussion simple and systematic, we'll start with our origin here. So the location of the centroid will be referred to this particular origin. Now, referred to this particular origin, the centroid of the red colored rectangle, if we recognize that this length is let's say W, and this length is H, then the centroid of the red colored rectangle would be at W by 2 and T by 2, where T is the thickness here. Similarly, we have the same thickness for this particular leg of the L cross section. So both these legs have thickness T. So the centroid of the red colored cross section would be at W by 2 and T by 2. What about the blue colored cross section? Well, this will have the centroid at H minus T by 2 and T by 2. Well, those are for the individual centroids. But what about the composite centroid of the entire cross section? To find that out, what we need to do is to just note that the z coordinate of the entire cross section would be calculated in this fashion. The area 1 times the z1 plus area 2 times z2 divided by a1 plus a2. So what we are doing here is to denote the area of the red colored rectangle as A1 and the z coordinate of its centroid as Z1. Similarly, we are denoting A2 to be the area of the blue colored cross section of the blue colored rectangle, and Z2 to be the z coordinate value of its centroid, that is the centroid of the blue colored rectangle. And of course A1 plus A2 represents the area of the entire cross section. So let us remind ourselves again that when we are writing these values of Z1 and Z2, we are basically referring to this starting origin here. So we are referring to this thing here. And you can note that we are thinking of something of the z-axis to be like this and the y-axis to be like this. So I think it will be better if we denote this by y dash and z dash. So that our Z1 will be actually Z1 bar and Z2 bar here. In exactly the same fashion, we'll have the y coordinate of the centroid as A1 y1 dash plus A2 y2 dash divided by A1 plus A2, where just as before y1 dash refers to the y coordinate of the red colored cross section and y2 dash refers to the y coordinate of the blue colored cross section, the y coordinate of the centroid of the blue colored cross section. Now whatever we have done here is follows from a fairly general idea that whenever we have any cross section composed of these sorts of rectangles, then we can have exactly the same kind of formula for the ZC, the centroid, and the YC for the centroid, by extending this not only for A1, A2, but possibly also for A3 and A4 if we have more such rectangular cross sections contributing towards the composition of the entire cross section. But right now we are only concerned with two rectangles making up the current cross section. Okay, so what do we do going forward? So the moment we have the values of ZC and YC, we can go ahead and identify the actual centroid of the whole cross section, which will be lying somewhere here. And what we need to do next is to set up our centroidal axis, the real axis which would be actually using to solve our problem. Because again, we remind ourselves that in order to use the mathematical framework to find out the bending stresses and the orientation of the neutral axis, we cannot use the y dash and the z dash axis. What we have to use is a pair of axes passing through the centroid. Okay. So this we denote as y and z. And whatever we do after this has to be in reference to this y and z axis. Now you please note that the zc and the yc values that we had found out is with reference to this starting origin, which was only a matter of convenience to understand the geometry. But the moment we set up our y-axis and the z-axis at the centroid, you note that referred to this new coordinate system, the coordinate values of the centroid are nothing but 0 and 0. So this centroid has the coordinates 0 and 0 referred to the y-axis and the z-axis, because that is where the origin lies. So now that we have identified the centroid and set up our coordinate axis at the centroid, our first job in our first step in solving problems is done. The next step is to find out the second moments of area. The second moments of area of the whole L-shaped cross-section. And in order to find out the values of the second moments of area, that is the IZ, the IY, and the IYZ, we'll again take the help of the idea that the L-shaped cross-section is composed of this red-colored rectangle and the blue-colored rectangle. And in order to go ahead, what we will use is directly the idea that we had been discussing in the previous page. So we'll be discussing this idea. So this is our motivation. So you see that when we have a rectangle, but we have to find out the IZ and the IY and the YZ referred to axes which are not passing through the centroid, which is the y-axis and the z-axis here. This is the idea that we are going to use in order to find out the IZ, the IY, and the IYZ for our rectangular cross-section here. So you see what we are going to do. So first of all, you consider this red-colored cross-section. We understand that the centroid of this red-colored cross-section would be somewhere here. So if we were to draw a centroidal axis solely focusing on this red-colored cross-section, it would be having its origin here. It would be having its origin here. Similarly, if we consider the blue-colored cross-section, then its centroid would be lying somewhere here. So this is the centroid here, and the centroidal axis for this particular cross-section would be having its origin here. Now, the pair of axes, the pair of axes that we are considering right now, for this particular cross-section having its origin here, it will have a certain distance from this z-axis, and have the y counterpart will have some distance from this y-axis. Similarly, the y and the z axis, which would be having their origin here, would be having some finite distance from this y-axis, would be having some distance from this z-axis. So we'll use these ideas and the idea that we discussed in the previous page to find out the second moments of area. So all that we need to do is to first consider the individual second moments of area of the red-colored cross-section and the blue-colored cross-section, and then using the parallel axis theorem, we can find out the actual second moments of area of the whole cross-section. So to give some concrete form to the ideas, let's actually draw the z-axis here, and let us draw the z-axis for the blue-colored cross-section. Let us denote the distance between this red horizontal axis here and the actual z-axis here by the distance dz1 . So this distance would be dz1, and this distance correspondingly would be dz2. Now writing the 2 in the superscript is not the best of ideas, because it can itself look like a square. So what we'll do is we'll put this within brackets here. Okay, so we can go ahead and draw similar distances between the corresponding y-axis, but that will only clutter up the figure more, and we only need to understand what happens for the iz, and we'll understand the whole thing. So for the iz, for the entire cross section, what we'll do is we'll first write down the contribution from the red colored cross section. That is the bottom one here. So let's say that the IZ1 denotes the second moment of area referred to the z-axis of the red colored cross section referred to its own red colored z-axis. But referred to the actual z-axis using the parallel axis theorem, we have to write this as the area of the red colored cross section times dz1, which is the distance between the two z-axes, square of that. Similarly, considering the contribution from the blue colored axis, what we'll have is IZ2. So this is the second moment of area of the blue colored rectangle referred to its own z-axis, that is the blue horizontal axis, plus its area, which we denote by A2, multiplied by the distance between the blue colored horizontal axis and the purple z-axis, which is this distance dz2, square of that. Okay, so proceeding in exactly the same fashion, we can write down the IY, and we can also write down the IYZ. So let's try to do that, even though it may clutter up the diagram a bit, but let's just go ahead with it. Okay, so again, coming back to this red colored cross section, this red colored rectangle, we have the y centroidal axis like this, and this distance that will be dy superscript 1. In exactly the same fashion, we'll have the centroidal axis referring to the blue rectangle like this, and the distance between them, between this y-axis and the actual y-axis that we have to consider, so this will be dy2. So now we can go ahead and write down the overall IY, which will be like this. First of all, we have IY1 referring to the red colored rectangle, the area A1 times the distance between the two y-axis, which is dy1 superscript, square of that, plus the IY two plus A2 dy2 superscript and square of that. So this is our IY. And finally, for our IYZ, we note that referred to the red colored vertical axis and the red colored z-axis, horizontal axis. So let me repeat, referring to this red colored triangle and the centroidal axis, which is this one. This is the vertical centroidal axis and the horizontal centroidal axis. Referring to these, the IYZ value is actually equal to 0, because as we can see from our previous page, when we had this kind of a setup where the axis were actually passing through the centroid of the rectangle, the IYZ value was equal to 0. So we use this idea here to note that the contribution to IYZ from this is actually equal to 0. So this is 0. However, we will have the contribution from the A1 times dy1 dz1. In a similar fashion, we also understand that IYZ2 would also be 0, but will still have a contribution from A2 dy2 dz2. So in this fashion, we can find out the values of IZ, IY, and IYZ. So if you are wondering that that in the previous lecture, when we were discussing the development of the mathematical framework, we really were discussing a lot about the mechanics of the whole situation. But in today's lecture, we have not been discussing at all about the mechanics. Rather, we have been talking solely about the geometry. And in real practice, when you have to deal with problems dealing with various kinds of cross sections, this is the first step that you need to complete. You first have to deal with the geometry. This is absolutely necessary. Unless you have a complete control over these formula, you cannot proceed to the mechanics part. So once these steps are done, it's fairly easy to plug in the values of IZ, IY, and IYZ in the formula for tan beta and the formula for the sigma xx, provided you have also been given the values of mz and my. So in an actual problem solving scenario, these two are very, very important steps. Now that we have gained some sort of idea about how to tackle problems involving this kind of a L-shaped cross-section, let's see how we can extend these ideas to other types of cross-section. We need not go through these individual steps like this, but we'll understand how these some other kinds of important engineering cross-sections can similarly be composed or thought of to be composed of such rectangles. Once we have that idea in a clean-cut form in our mind, then extending these ideas is fairly easy. So let's go to a next page. And let us consider some different cross-sections. So the first cross-section we'll consider is like this. So So this is a Z cross section, and just like before, we can imagine that we can make some cut here, and this Z cross section can be thought of to be composed of this rectangle, this rectangle, and this rectangle. And just like before, we can possibly start out by imagining that our origin is here, and we can find out the centroid of this Z cross section by referring to this starting origin, and then we set up our coordinate axis at the centroid and then proceed from there. In a similar fashion, we can have a cross section which is like this. And so this is sometimes referred to as a channel cross section, and this cross section can also be thought of to be composed of rectangles by making these two cuts. So we consider a rectangle like this, a rectangle like this, and a rectangle like this. So again, we can start off by imagining that our starting origin is here, and then we can find out the centroid of this whole cross section, and then after setting up our centroidal axis, we can proceed to find out the IZ, the IY, and the IYZ. And finally, we can have a very common engineering cross section widely used, which is the famous I section. So and again, we can proceed by considering this rectangle, and this vertical rectangle. Please note that unlike the other cross sections, this I section, it does have some nice symmetry associated with it, but it can still be subjected to some sort of unsymmetrical bending if the bending moments are applied on it in some kind of arbitrary fashion. And extending our discussion, we can have another section like the famous T section. So something like this. And just like before, we can have this rectangle and this rectangle. So in all of this, it is very much possible to find out the values of IZ, the IY, and the IYZ by referring to these red-colored horizontal rectangles and the blue-colored vertical rectangles. It is, of course, possible to have more complicated cross-sections, but these are some fairly common, some really common real-world engineering cross-sections. So, and you'll see that in many textbooks, these are the kind of cross sections on which most of the problems are based. But you see, as I had earlier discussed, the I section here, the T section here, they have some sort of symmetry This also has some sort of symmetry, but the L section that we had discussed earlier, this one, it doesn't have any symmetry, especially if you consider that W is not equal to H here. So if W is not equal to H, it really doesn't have any symmetry. So if you can get to grips with this L section, then you can get some idea on how to deal with unsymmetrical bending, considering all the general formulas. Now, because this is such an important topic, especially as it pertains to real-world engineering applications, what I've done is in the GitHub page of Advanced Mechanics of Solids, I have already uploaded a Jupyter notebook where there is a Matplotlib based GUI, graphical user interface, where you can play around with these values of the W, the H, and the T, and you can also play around with the applied bending moment to see how the centroid changes with changes in these lengths and how the values of IZ, IY, and IYZ changes. So what I have seen is that even when I was a student, going through these steps is so very tedious at times that students often get tired. I used to get tired while solving just one problem, because this involves so many calculations, as you can see. That after solving this thing, we never, if you're a little bit lazy, you'll never get any intuitive notion about the influence that these lengths, that these geometrical parameters can have. These are not like just some values that appear in some problems. These have some real engineering significance, the values of this W, the H, and the T. And my hope is that by using that Matplotlib based GUI in the GitHub page, and I'll provide the link below, you can develop a little bit of an intuitive engineering feel about the importance of these lengths as it pertains to the centroid, the values of the IZ, the IY, and the IYZ, without going through all the pain of these kinds of repetitive calculations. And my hope is also that someone may be encouraged to extend these ideas from the L cross-section to these various kinds of cross-section. So if we can have some Matplotlib-based GUI for these various cross-sections, it'll be really nice to have some kind of an intuitive feel about some very important engineering cross-sections. So that's it for today. So if you have any doubts, you can email me. I'll always respond to that. And the plan is that in the next lecture, we'll be going on to the topic of shear center. All right. Thank you very much.